Okay, so hello and welcome back. So in the previous video we talked about the intuitive idea of the derivative, and I think we talked about an hour about that, but I didn't try any real numerical values because the problem with that is that when you try numerical values while trying to explain some concept, for example, as big as the derivative, you saw that even when I wanted to basically as I tried to explain, for example, the concept of derivative without talking about the actual numerical values, it took me an hour or so to go through the concept, and I hopefully have understood the concept itself in that video. But then suppose that I had for example brought in the actual numerical values into that video as well, and then that would have taken us at least 2 hours to go through that concept. And when that happens, then you usually tend to not understand the concept itself, which is something that has happened to me many times. And I think this way it actually works in a much better and straightforward way. Now, hopefully you have understood the concept itself in the previous video. So what we are going to do in this video is that we are going to now I'm going to go over the same example one more time, but this time with the actual numerical values, and see what that translates to, because the numerical values are important in terms of understanding the limit. So that's basically what we want to do now. Now, suppose that having the exact same situation before, we had basically this cliff over here, and we said that we had basically, this was the top of the cliff right here, and then this was the surface of the ground. And then you take your stone up here and then hold it here. Your piece of stone is up here and you hold it here, and then you let it go. And then the stone will start falling towards the ground, and then it will basically it will have to cover this distance in this amount of time, or you could say this distance in this amount of time, however way you want to consider that. Now in this example, I'm going to have to basically go based on the book, because otherwise I would have to do a whole lot of calculation here, because the equation is S is equal to 4.9 t squared. So this is not a straightforward equation, and I would have to do a whole lot of squaring and multiplication, so I don't want to. I will do everything based on the book, but hopefully you will make sense of the numbers. Now, we said that physical experiments have confirmed that the body dropped from a tall cliff from over here covers a distance of 4.9 t squared meters in t seconds. So a body dropped dropped a high cliff like this from a tall cliff like this, it covers a distance of 4.9 t squared meters in t seconds, meaning that your S will eventually be in meters, and your t is going to be in seconds. And this is going to be the distance that the stone covers in, for example, or the object covers in basically t seconds. This 4.9 t squared is the distance in meters. Meaning that you can say that the distance, the distance basically S in meters covered by the body as a function of time and of course, to understand this part that says as a function of time, you would need to understand the concept of a function pretty well, and if I were to talk about this part, then would need another at least one even more than 1 hour to talk about this simple part over here, because the concept of a function is a whole bunch of basically definitions and things like that, which you cannot really which needs to be understood. So if you think that you don't understand what for example distance is in meters as a function of time, you do need to basically, of course I don't have any videos on functions, but I think it's enough to say that, for example, when you have, let's say that you have, for example, suppose that you have, for example, a car over here. Suppose that you have a car over here. The car starts from this point. And it basically, it keeps moving along this road, straight road, and ends up over here. Now, this is no usual car, but bear with me, I'm not very good at drawing, really. So now suppose that, for example, of course you know that if I take this point as zero distance, then suppose that the distance of this car along this road at any moment in time is given by this equation. For example, is given by S is equal to, for example, S is equal to, for example, I don't know. S is equal, for example, to t squared. Or let me make it simpler. Suppose that the distance of this, that the distance is given by, for example, S is equal to 2t. Meaning that at any time t, basically you have to basically multiply your t by 2 to get to the position of the car along the road. Meaning that for example, at t is equal to 1, let's say that this is t is equal to 1, the position of the car along the road is for example 2 meters, for example. Over here this corresponds to 2 meters. When t is equal to 2, the position of the car, if suppose you could read it along the road, and that would be 4 meters. at t is equal to 3 seconds, for example, the position of the car would be 6 meters, and so on and so forth. Then in that case, what you could do, t is equal to, s is equal to 2t. In that case, what you could do, you could basically write this as, for example, y is equal to 2x, y is equal to 2x, and that would be, for example, this line over here. That would be this line over here, a straight line, basically with a slope 2. A straight line with slope 2. So what this slope, for example, here specifies is basically is that coefficient by which time has to be multiplied at any point in time to get to the position of the car. For example, at this point, time has to be multiplied by 2 to get to 2. At this point in time, time has to be multiplied by 2 to get to 4. At this point in time, time has to be multiplied by 2, 3 times 2 to get to the position of the car, which is equal to 6, and so on and so forth. And as you can see, the velocity of this car is constant. The velocity of the car is constant, is not changing, because it's a straight line. Wherever you go along this straight line, basically the slope of this line is basically the same, meaning that at any point in time your velocity is the same thing. Now in this situation, what happens is that we basically on this axis we have y, or we have basically s over here. On this axis we have t, or we have x, or we have t over here. And you can see that this axis over here is called the dependent variable. It's called the dependent variable. This axis over here is called the independent. No. This axis over here is called the independent variable. It's called the independent variable. This axis over here is called the dependent variable. What that means is that your dependent variable, which is the distance covered by the car, is dependent upon time. The more time that you have, the more distance you will cover. So your distance is dependent upon time. And so you can say that basically distance is dependent upon time. So distance is the dependent variable, and time is the independent variable. Now in this situation, we can say that distance is a function of time. Is a function of time. And what that means is that if I were to make it very simple, not introduce so many basically definitions and things like that, there is something called the vertical line test. There is something called the vertical line test. And what the vertical line test is, basically you use a vertical line parallel to the y-axis, and you just slide this through the whole domain of the function, starting from negative infinity all the way up to positive infinity. And as you can see, as this line goes through the graph of this function, at any point in the domain of x or t, the line is going through the graph of the function only at one single point. At this point, at this point in time, it will be this point. At this point in time, it will be this point. At this point in time, it will be this point, and so on and so forth. And you cannot find any, not even one single moment in time where our vertical line is going through the graph of the function in two different points. And if that is the case, then you can call this relationship between x and y, you can call it a function, meaning that at any point in time, this relationship between x and y, for any distinct input, you are having a distinct output related to that input. At this input, again the same story. At this input, again the same story. Again the same story here. But suppose that you had, for example, something like this over here. Suppose that you had a parabola, something like this. Now if I do the vertical line test in the case of this parabola, you can see that for this input, this relationship between x and y is giving me two outputs for that input. And then I wouldn't know which one to take. Meaning that, for example, if this was time and this was the distance of the car from some point, then at this point in time, I wouldn't simply know if the distance of the car from that point is this output or this output over here. So this is not a function. This is not a function, and it does not pass the vertical line test. Pass the vertical line test. But on the other hand, this over here, is a function, and it does pass the vertical line test. Okay. So in this case, I can say that y is a function of x. X is my independent variable. Y is my independent variable. Over here, y is not a function of x. This situation over here is not a function of x. But if I had my parabola, for example, something like this, then in this case this would be a function, because this would pass the vertical line test, basically. So that's in short is the concept of a function. Meaning that's what it means when we say that basically the distances in meters covered by the body as a function of time. That means that S is your dependent variable and T is your independent variable. Depending on the values that you enter for T, you will have some values basically for S. That's all that it means. Now for this, now of course basically based on this relationship that you have over here, you will have some distances over here depending on time. For example, suppose that for example t is equal to 1 second. Then if t is equal to 1 second, then s is going to be equal to for example 4.9 meters. If t is equal to 2 seconds, then s is going to be equal to 4.9 times 2 square meters. If t is equal to, for example, 3 seconds, then s is going to be equal to, for example, 4.9 times 3 square meters, and so on and so forth. So in the same way, what I can do is that I can, of course, this color is not the best color I've ever chosen in my. So what I can do is basically I can basically in the same manner I can prepare a table of these values of some inputs t and some outputs basically s, which is going to be something like this. Now I'm trying to not rush myself so that you can understand the concept well. So suppose that, for example, you have a table over here. Suppose that this is, for example, your t and this is your s, and when basically your relationship is s is equal to 4.9 times t squared. So when t is equal to 0, then of course your s is going to be equal to 0, because 0 is being multiplied by 4.9. When t is equal to 1, your s is equal to 4.9. If you do the calculation here, you'll get the same values here. Of course, I'm writing these values only based on some table that has been prepared in the book. Okay, so now for the rest of these inputs and outputs, for example, if your t is, for example, 1.5, your output is going to be 11.025, input 1.8, your output is going to be 15.876, at input 1.9, your output is going to be 17.689, 1.95, 18.63225. At input 2, your output is at 19.6. 2.05, your output is at 20.59225. Okay, so I was talking, I had to stop this video. So input 2.1 was 21.609. 2.121.609. 2.2, for example, you have 23.716. 2.5 is 30.625. 3 would be 44.1, and 4 would be 78.4. And that's basically all the values that we have here. Now, of course, you can basically, like what we did basically in the previous video, you have basically all of these inputs over here and all of these outputs over here. So what I can do is that I can take, for example, any input from here and the corresponding output. For example, I can say that when t is equal to 1, s is equal to, for example, 4.9. S is equal to 4.9. And when t is equal to 4.9, for example, I'm sorry, when t is equal to 1.95, for example, then s is equal to 18.63225. So now I have these 2 points on the graph of the function, meaning that if I drew the graph of the function, I would have, for example, some function like this, and then suppose that this is t is equal to 1, this point over here, and the output over here would be 4.9, and then I have basically this input over here, for example, t is equal to, for example, 1.95, and then the output over here would be 18 point, for example, 63225. So now I have these 2 points, for example, on the graph of the function, and I have many more points that I have created over here, prepared over here. Now, in order to find the average velocity of that object between these 2 points, what I can do is that we said that basically the average velocity as definition is the change in basically change in distance over change in time. If you don't understand this definition, you can always think about that car going along that straight road. For example, as t is equal to 1, for example, or t is equal to 0, your car is at this position over here at s is equal to 0. When your t is equal to, for example, some value like 10 minutes, for example, then the car is at this position, for example, s is equal to, for example, 10 kilometers. So naturally, logically, what you would do, you would say that the car has covered this distance of basically 0 to 10 kilometers, which is 10 kilometers, over in a time frame of 10 minutes. And so you can write this as basically 10 minus 0 over 10 minus 0. Of course, I should have, for example, written this as, for example, 8, so that you don't get confused by this definition. T is equal to, for example, 10 minutes. And then this would be 10 minutes. So in 10 minutes, it's covered the distance of 10 kilometers. That means that this is 10 minus 0, and over here you have 10, oh, I made the same mistake again, I'm sorry. It's, let's say in 8 minutes, it's covered the distance of 10 kilometers. Then you can say that the average velocity of the car during this trip was 10 kilometers in 8 minutes. Or you can, of course, simplify this, for example, to 5/4 kilometers per minute, meaning that in every 4 minutes, it's covered the distance of 5 kilometers or something like that. Now you can write this fraction as 10 minus 0 over 8 minus 0. And So this is the change in distance, and this is change in time. Now over here you can see that the change in distance is basically, this is your distance. So this over here is vertical change. And change in time is along this axis. So this is horizontal change. So vertical change to horizontal change is nothing but y2 minus y1 over x2 minus x1, which is incidentally also the formula that we use for finding the slope of a line. So what that means is that if I find the slope of this line, this line segment over here, that means that I have found the average velocity of this object between t is equal to 1 and t is equal to 1.95. I hope that you have understood this whole thing over here. So we can conclude that we can use the definition average velocity is equal to change in distance from here all the way up to here over change in time, which is basically from here all the way up to here. So you have to divide this by this, which is basically nothing but the slope of this line. So then what I can do is that basically, for example, take these values over here, the average velocity v, some people call it v bar, some people call it v. That's of course only important in physics, not for what we are doing over here. So your change in distance is, for example, 18.63225 minus 4.9 over basically 1.95 minus 1. Over here t is equal to 1. So that is your average velocity. Now, so this way I can use this table. To calculate the average velocity of this object between any two moments in time, between 1 and 1.95, between 1 and 2.05, and so on and so forth. But now, as we discussed before, what I really care about is that basically the average velocity is not enough for me, because I want to know, for example, if the object, if I take, for example, the average velocity between this point and this point in time, I know the average velocity between these 2 points, but I don't really know what the average velocity of the object was at this point exactly in time. That sort of thing I could not know using the number that I get for the average velocity. It's not possible. It just gives me some average number for the whole thing put together, not any points in specifically. So what I care about is some specific point in time, and I want to know the average velocity at that exact point in time, which I could call, for example, the spontaneous, I'm sorry, not spontaneous is not the right word, instantaneous velocity. The instantaneous velocity. So the average velocity, when you look at it at a very specific point in time, becomes instantaneous velocity. That's what we want to do. And what we want to calculate here now is find the instantaneous velocity at this point in time at t is equal to 2 seconds. That's what we want to do. So as you remember, what we did before was that if this was the graph of the function, what we did was that we took some point over here and some point over here, and then we found the slope of this line, and that was the average velocity during this trip from here all the way up to here. And then what we did again, we got a little bit closer to this point, and then basically try this point over here, and this was basically then the average velocity for this shorter trip. Then again we got a little bit closer to the other point, and we calculated the slope of this line, and that was the average velocity between these 2 points, and so on and so forth. So we can do the same thing for the data that we have here. We can pick, for example, this point as, for example, t is equal to 2, and get closer and closer and closer to 2 until we kind of close in on 2 enough so that we can call that average velocity the instantaneous velocity, meaning that we have to close in on this point t is equal to 2 so much so that the 2 points, like that, for example, these 2 points, this point has to get closer and closer to this point, so much so that the 2 points become exactly 1 point on the graph of the function. And then at that point, basically the line, the slope of the line becomes just the line, the secant line, or this line over here becomes just a line that is just touching the graph of the function at just 1 point over here. That's basically what we want to do. So what that means is that I can start, for example, with 19.6 and 0. So I can start, for example, from here. So this point over here becomes the point that I have down here. This point over here becomes the point that I have down here, and these points become basically the points that I take over here and get closer and closer and closer to this point. So this is basically that point over here. Now what I need to do is, for example, calculate the average velocity between t is equal to 0 and t is equal to 2. Average velocity between t is equal to 0 and t is equal to 2. And that is basically that would be basically s related to t is equal to 0 is equal to 0. S is equal to 0 here, and over here s is equal to, for example, 19.6. So I can write the average velocity is equal to 19.6 minus 0 over 2 minus 0, which gives me 19.6 over 2 meters per second. Remember that the distance was in meters, and the time was basically in seconds. So this becomes meters per second, which is the same thing as, of course, 9.8 meters per second. Okay. And well, of course, I can get a little bit closer to this point, meaning that I can come over here, and then the average velocity between t is equal to 1 and t is equal to 2 would be basically v is equal to, basically at this point, your s is equal to 4.9, and at this point your s is equal to 19.6, and so you can write 19.6 minus 4.9 over t over 2 minus 1 is equal to of course I'm not doing the calculations here, but 14.7 meters per second. So you see that the average velocity over here was 9.8, over here is 14.7 meters per second. The average velocity is changing when you change the time frame or when you change the time interval. And well, if you keep doing the same thing for all of these points over here with this point as a reference point, you will get a table. Like this. Now this is actually the very process of calculating the derivative. So suppose that I take this point as the reference point, and then I try this point, and then this point, and then this point, and so on and so forth. So then I can say that basically I can call this the average velocity, v, and I can call this point t1, for example. This I will take as t2, and then all these points would be basically t1. So this could be your t1 at one point in time, this could be your t1 at one point in time, and then you can change your t1. So for example, when your t1 is equal to 0, we calculated this value, the average velocity, it gave us 9.8 meters per second. When your t1 was 1, it gave us some value like 14.7 meters per second. And then in the same way you can calculate them for all of these t1s as well. For example, 1.5 or also 1.8 or 1.9 or 1.95 and also 1.99 you can calculate as well, although it's not over here. You can calculate 1.99 as well. So the respective values for these inputs would be 17.15, 18.62, 19.11, and 19.355 and 19.551. Okay, so these are the average velocities. I was comparing these numbers to these numbers over here, but these are actually different things. There is no need to compare these numbers really. So what you see from this table, you observe that the average velocity is gradually, of course, increasing from 9.8 to 14 to 17, 18, all the way up to 19.551. And as you can see, as I'm moving in this direction in this table, I'm making my time intervals smaller and smaller. For example, over here, this average velocity is related to some average velocity between t is equal to 0 to t is equal to 2. Over here, this is an average velocity for a time interval between t is equal to 1 and t is equal to 2. So this is basically 2 seconds. This is 1 second. Over here you would have 0.5 seconds, and so on and so forth. So you can see that as you are moving in this direction in this table, you're getting closer to this point, meaning that you're making the time interval between the 2 points smaller and smaller. And well, of course, what that also means is that as you're getting closer and closer to t is equal to 2, you're getting a better and better idea as to what the velocity is as at t is equal to 2. You can see as you're moving towards basically, as you're making the time intervals smaller and smaller, basically these numbers are kind of tending towards one single number, like 19.11, 19.355, 19.555, and so on and so forth. It's around 19.5 or so. Now this is all good. This is all good, but over here, I mean, by this process, the problem with this process is that I'm not allowed to basically calculate the exact velocity at t is equal to 2. And the reason for that is that, suppose basically by this process what I'm doing, I'm just picking some points in time over here and getting closer and closer and closer to that number, meaning that I can go all the way up to 1.999999 and so on and so forth, like a million, for example, nines over here. But I cannot make this number 2 exactly, because if I make this number 2, then the average velocity would be the change in position, and then so the change in position over the change in time. Now the problem with that is that the problem with getting very, very close to the point t is equal to 2 and making your point exactly t is equal to 2 is that basically then if I get close enough to t is equal to 2, so that you see what I'm doing over here is that basically if this is the graph of my function, suppose that this is t is equal to 2, and I'm picking these points over here, getting closer to this point, closer and closer and closer, and so on and so forth. Now if I get close enough to t is equal to 2 so that this point becomes exactly t is equal to 2, then of course the change in position would be 0. Change in position would be 0. And the change in time would also be 0, because then there is no time between t is equal to 2 and t is equal to 2. And then you would end up with 0 over 0, which is of course not this is called indeterminate. This is called an indeterminate form, or I might be wrong about this, but some name like this, which has to be resolved. I mean, this kind of thing is really doesn't really mean anything in mathematics. It has to be some number, but 0 by 0 is not really defined. So what that means is that even if I get very, very close to 2, I would not still be at 2. There would still be some time. There would still be some time. Of course, I'm picking these values from here, not from there. I apologize for that. I'm picking these values from the lower. Okay, so I apologize. I had to pause this video. I got a call from a friend. So we came all the way up to the point that basically if I got very, very close to 2 from this side, for example, if I got close enough to 2 so that the point becomes exactly 2 itself, then I would get into into the indeterminate form, which is not really something nice in mathematics. Mathematicians, they don't like this form, which is, I suppose it's called indeterminate form, if I'm not wrong. Let me see. Okay, so 0 divided by 0, you see it's called indeterminate form. 0 divided by 0 is indeterminate. So then you have to somehow, suppose that I got very close to 1.99, I'm sorry, very close to 2, I would still not be at 2, and there would still be some time between, for example, suppose that I got to 1.9999999999. There would still be some very tiny fraction of time between this point in time and 2, and then basically my goal over here is that I want to assume that since, for example, of course, if I took the t1 as this time, t1 is equal to this, and t2 is equal to 2 seconds, since there is a very tiny amount of time going basically between these two time points, then since the distance between these two time points is very tiny, it makes logical sense, and it would be a safe assumption to make that between these two time points, nothing dramatic can really change in the average velocity of the object. And so then I could say that, for example, the average velocity between t1 and t2, I could take it as the instantaneous velocity at t2. Now this is assuming that nothing dramatic really happens between this point in time and t is equal to 2 seconds basically. But still, you cannot know that. I mean, you have to just make this distance smaller and smaller and smaller and smaller, but you couldn't still get to the number 2 itself, because then you would get into the indeterminate form. So now mathematicians have done something very clever in order to resolve this problem of getting very close to 2 and still not get into the indeterminate form. And what that is that now we will talk about that in just a few moments. But now the next thing that we have here, so we can make the time intervals ending at 2 smaller. We see that we get a better idea of the velocity, hoping that nothing really dramatic happens between 1.9. Conclude that it's just 19.51. So then, based on this table that we had over here, at basically between 1.99 and t is equal to 2, the average velocity, we calculated that to be 19.551 meters per second. So assuming that really nothing really wacky or dramatic really happens between this time point and this point in time, then I can assume that 19.551 is actually the velocity at this point in time, t is equal to 2. I can make that just as an assumption. And then in order to make sure that that's actually the case, what I can do is that I can, of course, since I have some data over here, I can actually do the same thing for the other side of the data that I have, meaning that I have the at t is equal to 2 seconds, the distance is known to me, and for some other points in time after t is equal to 2, I have some data over here as well based on the formula that I had, and so I can calculate some average velocities for this side as well, meaning that now basically in this table, what I did was that I calculated the average velocity between this point and this point, and this point and this point, and then this point, and so on and so forth. So now I can do the same thing for this side. And so if I do so, I will get another table for the other side of 2, which is, I call this, for example, T2, and I call this, for example, V. And then I can start from, for example, 4 to 3 to, for example, 4, and then I can go to, for example, I can have 3 over here, I can have 2.5 over here, and I can have 2.2 over there, 2.2, and then I can have 2.1, and then I can have 2.05, and then I can have 2.01, and of course 2.01 we have added over here because we wanted to get a little bit closer to 2 from the right, basically. And well, I'm cheating here because I'm writing these values from the book, but for the value 4 you're going to get 29.4, 24.5, and then you have 22.05, and then you have 20.58, and then you have 20.09, and then you have 19.845, and then you have 19.649. Okay, so you can see that as I move from this side, starting from 4, moving from this side closer and closer to 2, you see that for basically for example, over here you have the time difference between this point and t is equal to 2 is equal to 4 minus 2 is equal to 2 seconds. Over here you have 3 minus 2, which is equal to 1 second. 2.5 minus 2 is equal to 0.5 seconds, and so on and so forth. You're getting closer and closer, and the time interval is getting smaller and smaller over here, until you get to this value, which is very close to 2, meaning that the difference is 1/100th of a unit. And you can see that excuse me, you can see that the average velocity over here becomes 19.649. Over here the average velocity on this side was 19.551. Over here is 19.649, and 0.5, 0.6 or so. There is not much difference between the two. So what I can conclude from this situation is that the average velocity, or V, is somewhere between 19.649 and 19.551. 19.551. The average velocity must be somewhere between these two numbers, and there is not much difference really between these two numbers, only probably 0.9 of a unit, 9/10th of a unit or so. So now let me read the part over here, see if there is anything really necessary to explain here. So in the first set of computations, which was basically this, we have done what we have done is to find the average velocities in increasing time intervals ending at t is equal to 2, and then hope that nothing dramatic happens just before t is equal to 2. In the second set of computations, we have found the average velocities decreasing in time intervals ending at t is equal to 2, and then hope that nothing dramatic happens just after t is equal to 2. Purely on the physical grounds, both these sequences of average velocities must approach a common limit. Purely on physical, basically, on physical grounds. These values must approach a common limit. Meaning that probably what they mean is probably based on experiment or something like that. And I think Newton, for example, probably had the same kind of assumption, because he must have done, I don't know, many sorts of, he was a physicist, of course, and he must have done a couple of experiments, otherwise from this situation, that I don't know, that must be the same, the only way to conclude that, for example, the limit is supposed to be like that, otherwise there is no other way to know, really. So it says that purely on the physical grounds, both these sequences of average velocities must approach a common limit. This is important. We can safely conclude that the velocity of the body at t is equal to 2 is between 19.551 and meters per second and 19.649 meters per second. And well, we know that basically velocity is the rate of change of displacement, or the rate of change of distance from some point in your your coordinate system. Meaning that, for example, suppose that I take this as my coordinate system, and there is a car over here at t is equal to 0, and over here s is equal to 0, for example. Over here, suppose that t is equal to 10 seconds and s is equal to, for example, 12 meters or so. Now the car starts from here at s is equal to 0, ends up at s is equal to 12. Now if I have this, if I start at this point and come all the way up to this point, the basically 12 minus 0 is basically the change in distance, of course, with respect to some well-defined point in that coordinate system, and that is basically, of course, loosely translated, you could say that that is called displacement. And of course, so displacement is basically change in distance. So velocity, you can call it the rate of change of displacement. Or basically, if you want to understand this in a more, if you want to understand it in a better way, you can also say that the velocity is the rate of change in the way that basically an object changes its distance from some point, some well-defined point in the coordinate system. And a more sophisticated way of saying the same thing is, well, velocity is the rate of change of this displacement. That basically means the same thing. Hence, what we have accomplished is the following. From the given data of distance covered at various time instants, we have estimated the rate of change of the distance at a given instant of time. This is very, very, very important. This is very, very important. Please pay attention to this point. So what we have accomplished during this whole thing, that basically during this whole thing that we talked about, is that from the given data from the given data of distance covered at various time instants, distance covered at various time instants, we have estimated the rate of change of the distance distance at a given instant of time. At a given instant of time. So what that means is that from this data that we had, from the data that we had here, based on this relationship between distance and time, what we have accomplished is that from the given data of distance covered basically at various time instants, which is basically all of these distances over here, we have estimated the rate of change of distance, which is average velocity at a given instant of time, which is basically this estimate over here that we have made between, for example, these two numbers. And of course, I have already talked about this a few times and I've shown you this, but this is basically the same thing this is basically the same story that we have over here. And what that is basically, suppose that this was basically the equation that we had was S is equal to 4.9 times t squared. If you have this relationship between S and t, suppose that the graph of this function would be something like this. Now what we have done over here, we have taken this point, for example, in time, for example, t is equal to 2. We have taken this time t is equal to 2, and then we have basically during these two the two basically sets of calculations. Now I take it from the right, for example, meaning that the set over here which was related to this table over here, this table down here. We have taken, for example, some point over here. This would be, for example, some input, and then we have calculated the difference in time over the difference in distance. Again, I've come down over here. Again, difference in distance over distance in time. Over here, distance in time, the difference in distance, and you can see that there would be, what we calculated was basically the difference in distance over the distance in time would be the slope of this line. Then we calculated the slope of this line, then we calculated the slope of this line, until we got to some point which was very, very close to this point, and then we calculated the slope of, and of course that point was very, very close to this point, and you could imagine that the 2 points are actually one single point, really. And then this line becomes, for example, some line like this, which just touches the curve at this point, and this is called the tangent line. The tangent line. And this over here is called, any of these lines over here really is called the secant line. And so you can say that, and this is called the limiting process. So you can say that in the limiting process, in the limiting process, the slope of the secant line, becomes the slope of the tangent line which is the instantaneous velocity of the object, at some specific point in time. So that's basically the whole story behind the derivative. Now the only thing that we don't understand here, basically we came all the way up to this point where basically we got closer and closer to 2 from both sides, but still we don't have a good idea of how this basically we understand the process. We don't have anything. Basically, there is no. We understand everything about the process, but how the limiting process actually works, that we will find out in the next video. And then once we have understood the limiting process, basically the concept of the limiting process properly and algebraically, then we can basically put the whole thing together and then define derivatives and then start finding the derivatives of different functions. So I hope that you enjoyed this video. I will continue with the limits in the next video, and thank you.